Okay, so welcome to this next video in the playlist on voltage-gated ion channels, and we've just done the Nernst equation, and now what we're going to move on to is how you actually build up resting membrane potential across a cell membrane, because resting membrane potential is not the equilibrium potential for sodium, and it is not the equilibrium potential for potassium. It's a combination of the two. Basically, in cells, you have something more complicated happening than just the pure Nernst equation, because effectively what you have is two ions which can move across the membrane, sodium and potassium, and what you get is something slightly more complicated. And there is an equation which tells you what the resting membrane potential will be, and that's the Goldman-Hodgkin-Katz constant field equation. That couldn't fit in the title of this video, so I just put the Goldman equation, but that's the full name for it. Okay, so firstly, if we have a cell here, then the cell has a very high concentration of potassium inside it. So potassium is very, very high inside the cell, and sodium is very, very low inside the cell. So you have hardly any sodium inside, and you have a big concentration of sodium outside, and a small concentration of potassium outside. Okay, basically, if I draw sodium ions in orange and potassium ions in blue, then it looks like this. You have a few little sodium ions, then a lot of sodium outside, so a very high concentration of sodium in the extracellular fluid. And if we add in potassium now, you have low concentration of potassium outside and a very high concentration of potassium inside the cell, basically. Now, I'm going to draw this in a different way to discuss how you build up resting membrane potential across this cell membrane. And the way I'm going to draw it is I'm going to draw it like we discussed for the Nernst equation, as two chambers with a semi-permeable membrane in between. Now, I want you to realize that this model here, with the semi-permeable membrane here, is exactly the same, effectively, as the real cell. So the real cell is basically a semi-permeable membrane, a membrane that's permeable to not only sodium, but also potassium now. And basically you have two fluid compartments, an intracellular compartment, which I'll label as this one on the left, so this can be the intracellular compartment, and an extracellular compartment. And you may say, but we've got glass on these sides, surely that's different from this. And you're right, of course it is different, but as far as the exchange of ions is concerned, this is a good enough model for this, basically. And I just prefer working with a diagram that's a square rather than a circle, just because it feels nicer for some reason. Okay, so if we now transfer the information on this diagram into this diagram, we have very high concentration of potassium on the intracellular compartment, and a lower concentration of potassium on the extracellular compartment. And we have a low concentration of sodium in the intracellular compartment, and a high concentration of sodium in the extracellular component. Right. Okay, so there's another now important thing that we need to discuss. This membrane, the cell membrane here, this semi-permeable membrane here, it is permeable to both sodium and potassium, but its permeability is different for sodium and potassium. Basically, what you have little channels in here. You have two types of channel. You have sodium channels through which sodium can move, and potassium channels through which potassium can move. And basically, if a sodium ion hits a sodium channel, it is less likely to actually go through that sodium channel than if a potassium ion hits a potassium channel. Basically, the membrane is more permeable to potassium. It's easier for potassium to cross this membrane than it is for sodium to cross this membrane. And I'm not actually sure whether it's that the channels, the potassium channels are easier for potassium to go through than the sodium channels are for the sodium to go through, or whether it's just that you have more potassium channels, a higher density of potassium channels. That's an interesting question, but the point is that if, for a certain concentration basically, so if I draw another diagram out here, if I put a certain concentration of potassium in here, and I put the exact same concentration of, let's say, sodium in here as well, So we've got the exact same concentrations of sodium and potassium, and then I put the cell membrane here. What I would find is that the rate at which potassium moves through here, moves onto this side, is bigger than the rate at which sodium moves across here. So basically, even though their concentrations are the same in this experiment, the rate at which potassium crosses the membrane is going to be greater than the rate at which sodium crosses the membrane, because the membrane is more permeable to sodium. Okay, right, so I'll denote that by saying the permeability to sodium, which is denoted PNA, if you want plus there, is going to be less than the permeability to potassium. Okay, right. So now what we want to discuss is how we actually build up resting membrane potential across the cell membrane, across this membrane. Now, what happens is that you basically do the same argument as in the Nernst equation, but you do it for two ions now. So, what we can say is, if I bring this diagram down here, okay, so we have two compartments again. We have our cell membrane in the middle, which is permeable now to both sodium and potassium, but the permeability to potassium is greater than the permeability to sodium. So I'll put in these channels. And we have a very high concentration of potassium on this side, and we have a very low concentration of potassium on the extracellular component. And then it's the opposite way round for sodium, basically. You have a very high concentration of sodium out here, and a lower concentration of sodium inside. And I want to stress that the concentration gradient for potassium, i.e. how much bigger the concentration of potassium on the intracellular side is compared to the extracellular side, is about the same as the sodium gradient going the opposite way, i.e. it's about the same as how much bigger the extracellular concentration of sodium is than the intracellular concentration of sodium. Okay, so and of course we haven't mentioned that both of these would have counter ions. So both sodium ions and potassium ions are positively charged. They would have been put in with a counter ion. So they will have some maybe chloride anions in here which are partnered with them, the counter ion. So we would have started maybe with sodium chloride and potassium chloride. But the membrane isn't permeable to the chloride anions, so those don't move. Okay, so what happens is, because there is a greater concentration of potassium on this side, then the movement of potassium ions from the intracellular component to the extracellular component is greater than the movement of potassium ions from the extracellular component to the intracellular component. So basically you have a movement of potassium ions in both directions. You have potassium ions moving from this side to this side, from the intracellular to the extracellular component, and you also have some potassium ions, few little potassium ions, going from the extracellular component to the intracellular component. However, because the concentration over here of potassium is greater than the concentration of potassium over here, the movement from intracellular to extracellular is greater than the movement from extracellular to intracellular. Okay, so overall what you get is a net movement of potassium in that direction. Okay, now what you also have is, because sodium concentration is much higher in the extracellular component, you have a movement of sodium from the extracellular component to the intracellular component, which is bigger than the movement of sodium from the intracellular component to the extracellular component. And that's again just because you've got a bigger concentration of sodium here, so the probability that a sodium ion is going to move from this component, the extracellular fluid component, to the intracellular component is going to be bigger than the probability that these smaller concentration of sodium over here, which is denoted by this these orange dots, is going to move from the intracellular to the extracellular. So basically, overall, what you get is a net movement of potassium in this way. So now this arrow denotes the net movement, so it denotes this arrow minus this arrow, and this arrow, and you also have a net movement of sodium this way. And again, that one denotes this arrow, the bigger arrow, minus the littler arrow. So effectively, it's like adding vectors. Okay, so what overall you have is you have a net movement of positive charge in the form of potassium ions into the extracellular component, and you have a net movement of sodium ions, positive charge in the form of sodium ions, from the extracellular component to the intracellular component. However, the concentration gradients are basically the same for the sodium and the potassium, but the membrane is more permeable to potassium than it is to sodium. So overall, the net movement of potassium ions from the intracellular to the extracellular is greater than the net movement of sodium ions from the extracellular to the intracellular. So basically, the number of sodium ions that are going to move from here to here, overall, the net movement of sodium ions, so basically sum both of these up and take what overall happens, is smaller than the net movement of potassium from the intracellular to the extracellular component. So overall, what happens is that you move some sodium ions from this side to this side. So how am I going to denote that? You move some sodium ions from this side to this side, and you move more potassium ions basically from the intracellular component to the extracellular component. So now in this diagram, all I've shown is which ones have moved basically. So you've moved some, this denotes the amount of sodium that you've moved from here to here, and this denotes the amount of potassium that you've moved from here to here overall. So basically what happens is that you build up a positive charge on this side, because overall you have moved more positive charge from the intracellular to the extracellular side than you have from the extracellular side to the intracellular side. The potassium beats the sodium basically, and you overall get a positive charge on this side and a negative charge on that side. Now basically this continues building up until you reach an equilibrium, because what happens is that as you gradually build up this positive charge, as you gradually build up the positive charge on this extracellular side, it becomes more difficult for these potassium ions on the intracellular aspect to move to the extracellular component, because they're being repelled by the positive charge. If you've watched the Nernst equation videos, it will be because they have to now have a certain amount of energy to move up the electrical potential difference. So if we call this the electrical potential of the extracellular component, and this the electrical potential of the intracellular component. Now, generally when people say the voltage across a cell membrane, what they mean is the voltage from the extracellular component to the intracellular component, i.e. they mean how much bigger is the intracellular component electrical potential than the extracellular component. So basically that's why we usually say that the resting membrane potential is negative 65 millivolts, because we're asking what's the difference between how much bigger is this one than this one. But of course this one's negative, so you end up with a negative difference, i.e. this one is negative 65 millivolts of the extracellular one. And that, you can see how that's going to come about by this. Okay, so gradually what happens, as you move more potassium ions over here, what's going to happen is that it's going to become more difficult for these potassium ions to move from the intracellular component to the extracellular component. So basically that arrow of movement of potassium from the intracellular component to the extracellular component is going to get smaller. Okay, and the movement from extracellular to intracellular is going to remain roughly the same. Similarly, the movement of sodium ions from the extracellular to the intracellular is going to remain roughly the same, because it's not affected by this electrical potential problem. In reality, it's going to get slightly bigger, because it's going to be pushed away by this positive charge, the sodium ions. But in the derivation of the Nernst equation, we didn't actually factor in that consideration. We just factored in the consideration that the movement of the ions from the intracellular side to the extracellular side is going to get smaller, basically, because of this positive charge. And similarly, in the derivation of the Goldman equation, we're going to also only factor in that consideration. And because this is getting more positive charge, again, the movement of sodium ions from the intracellular to the extracellular, this arrow here, is also going to get smaller. Okay, so what will overall happen is that the movement of sodium, the net movement of sodium from the extracellular to the intracellular is going to get bigger, because this one, the movement of sodium from the extracellular component to the intracellular component, has remained roughly the same. But the movement of sodium ions from the intracellular to the extracellular has gone down, because now these sodium ions, which are going to move from the intracellular to the extracellular, have to have a certain amount of energy, because they're going to go up the electrical potential gradient. Okay, so because you've got less moving this way overall, that means that the total movement in the opposite direction has gone bigger. So the net movement of sodium ions increases. And because the movement of potassium ions from the intracellular to the extracellular has gone down, and the movement of potassium ions from the extracellular to the intracellular has remained roughly the same, then the net movement of potassium from intracellular to extracellular goes down. And basically what will happen is that you will continue moving overall net positive charge into the extracellular component over the intracellular component, and that will continue building up this positive charge over here. So this voltage will get bigger and bigger and bigger until this is big enough, this electrical potential difference between the extracellular fluid and the intracellular fluid, this electrical potential difference is big enough that it reduces the net flow of potassium from the intracellular to the extracellular component enough that the net flow of potassium is equal to the net flow of sodium backwards. And at that point, you get an equilibrium, basically. That is the point of equilibrium in a resting membrane potential cell. So what you will notice is that it's an electrical equilibrium. It's the point at which the movement of charge from the intracellular component to the extracellular component matches the movement of charge from the extracellular component to the intracellular component, i.e. the number of positive ions that you are moving in the form of potassium from this side to this side is equal to the number of positive ions which you are moving from this side to this side in the form of sodium. And that's the important thing, that this is not, this is the resting membrane potential is this equilibrium point of movement of charge, not the equilibrium point of movement of sodium ions or potassium ions. Basically, what you could do is you could work out what the Nernst potentials for sodium and for potassium are in this case. So you can work out, often denoted, the equilibrium potential for sodium and the equilibrium potential for potassium. And basically, they turn out to be something like, I think this one's about plus 67 millivolts if you put in the correct concentrations of sodium that are across the cell membrane, and potassium something like minus 90 millivolts, something around there. Basically, resting membrane potential is not equal to those. So at resting membrane potential, you still have a movement of potassium and sodium. If you leave it, once the cell reaches resting membrane potential, then the movement of charge is non-existent, i.e. the movement of charge in the form of potassium this way matches the movement of sodium this way, and therefore there's no net movement of charge across this membrane, but you are still moving potassium from this side to this side, and sodium from the extracellular component to the intracellular component. So that's eventually going to drain it's going to drain potassium into this side and drain sodium into that side. So you have to have something to return to restore the concentration gradients, and that is the role of the sodium-potassium pump. So if I put in here is the sodium-potassium pump, and basically what the sodium-potassium pump does is it moves sodium from the intracellular component to the extracellular component. So it moves sodium this way, and it moves potassium from the extracellular component back into the intracellular component. So it reverses this net movement of potassium from the intracellular to the extracellular component. So basically you're going to move the potassium, the resting membrane potential, the equilibrium potential is just going to move potassium from the intracellular to the extracellular component, and then the sodium-potassium pump is going to reverse that, and also, at resting membrane potential, you will have sodium being moved from the extracellular component to the intracellular component, and again, the sodium-potassium pump will reverse that movement. So that is the role of the sodium-potassium pump. It's there to reverse the movement of sodium and potassium that is occurring at resting membrane potential. Its role is not, I repeat, is not to build up the resting membrane potential. The resting membrane potential comes because when you put these starting concentrations in, you have a net movement of potassium from this side to this side, which beats the movement of sodium from this side to this side, and therefore you overall move positive charge into this side. And I also want to stress that, just as in the case of the Nernst equation, the amount of charge the amount of potassium ions that actually move onto this side is tiny. It's absolutely tiny, so you can approximate the concentrations as though they are constant, i.e. the concentrations remain at what they were originally, and basically the sodium-potassium pump assures that they do remain, because if the sodium-potassium pump was not there, eventually what would happen is you'd move loads and loads of potassium onto this side, and you'd move loads and loads of sodium onto this side, and then concentrations would all go pear-shaped. But that's the role of the sodium-potassium pump, to retain the concentrations as they were originally. And basically, this tiny movement of positive charge onto that side, you don't need to worry about the concentrations having changed because of that. So you can put in the Goldman equation the final values of the concentrations. You can put in the initial values that you started with, and we'll call it there for this video and continue on in the next video.